Hi, my name is Jonas and I welcome you to this video on the use of sensor fusion and observers in mobile robot control. Let us first look at some examples that show us why we might want to use an observer. Say we want to get the position from an accelerometer by integrating the acceleration twice. If the measured acceleration matches the reality, then this works fine and we get the position. However, we usually have some noise on the signal or the signal might have an offset. In the picture on the left, we see the difference between the measured and the true acceleration in blue. The signal has an offset of 0.1 meter per second squared and white noise. The effect on the velocity and position can be clearly seen. Both drift away rather quickly. Another case could be that we want to determine the velocity of our mobile robot by differentiating the wheel position. However, due to the finite resolution of the encoder, the measured position signal is discretized. And if the resolution is not high enough, then it is impossible to determine the velocity. In the example on the right, the discretization is barely visible if we look at the position signal. But this is no longer the case if we look at the velocity signal. As a last example, it could be that the bandwidth of the sensor signal is not high enough for our desired control frequency. As an example, if we get a new position from our GPS sensor every second, then we cannot use the signal to precisely control the robot's movement because we are essentially blind in between the new measurements. But how can an observer help us to deal with these problems? Let's go back to the first example with the accelerometer. Here we have a controlled system. A force acts on the system which results in an acceleration of the system. We would like to know the velocity of the system, but we only have an accelerometer and an encoder. Therefore, we cannot directly measure the velocity. Unfortunately, the accelerometer signal is noisy and has an unknown offset which leads to a drift in the calculated velocity. On the other hand, the resolution of the encoder is not good enough to get the velocity by differentiation. In this case, we can use an observer to fuse the two signals together. First, we calculate the difference E between the position signal from the encoder and the accelerometer. We feed this difference into a controller and get an acceleration, which we can then add to the measured acceleration. From our previous video on control, we know that we can use a PD controller for this. The structure of the PD controller is shown here once more. To calculate omega 0, we can define a time constant tau. Omega 0 is then 1 over tau. The damping constant d can be chosen as well, but usually 0.7 is a good value. Here we see the results of the observer for different values of the time constant tau. In blue we see the velocity signal derived from the encoder. We can clearly see the discretization problem. In red we see the velocity from the accelerometer. We can again clearly see the offset and drift of the signal. In yellow we see the output of the observer and in purple the true velocity. If the time constant tau is set to 0.5 seconds, the observed velocity almost perfectly follows the true velocity signal. But if the time constant is set to 0.005 seconds, then the dynamics of the observer is too high and we see some of the discretization error in the resulting velocity signal. On the other hand, if the time constant tau is set to 10 seconds, then the signal is very smooth but does not anymore follow the true signal as well as before. As an alternative to measuring the acceleration with an accelerometer, we could also calculate the acceleration with the motor model and the inverse mass matrix and use the signal in the observer algorithm. The problem here is similar, but instead of noise and an offset, we have some inaccuracies in the motor model and the mass matrix, which lead to a drift in the calculated velocity signal. Instead of a simple PD controller, we can also use more complex algorithms such as a Kalman filter. But we will cover this in another video. So far, we have been looking at different examples for local sensors. However, usually we also want to know the position of the robot in respect to its environment. We can still calculate the global position by measuring the wheel velocities and calculating the global position using the forward kinematics and odometry, but this calculated global position has a drift and offset. To correct the position, we can use a global sensor, for example a LiDAR. As we've seen it before, we can calculate the difference E between the position measured with the global sensor and the position from the odometry. For the controller, we can simply use a gain with the value 1 over tau and define the time constant tau as we like. Let's bring this into the context of our mobile robot kinematics. Here we see the forward kinematics and odometry and where we must connect our observer. One problem that we often face is that some global sensors do not provide the orientation. This can cause problems because then we can only observe the position, but the orientation of the robot can slowly drift away. Thank you for following me through this video on sensor fusion and observers, and I will see you in the next one.